Welcome, my friends. In this video, we will be discussing the rational zeros theorem, but first we need to talk about a simpler theorem called the factor theorem. The factor theorem says that if r is a zero of a polynomial, then x minus r is a factor. The factor theorem can be a useful tool for factoring polynomials of higher degrees. For example, consider the polynomial f of x is equal to x to the third power minus 2x squared minus 29x plus 30. If I plug in 1, I get f of 1 is equal to 1 minus 2 minus 29 plus 30. 1 minus 2 is negative 1, minus another 29 is negative 30, plus 30 is 0. That means x equals 1 is a 0 of this polynomial. By the factor theorem, that means I know that x minus 1 is a factor, and therefore can be factored out. How specifically do we factor out x minus 1? That's where synthetic division comes in. Recall that if x minus 1 is a factor, that means we can put the number that makes x minus 1 equal to 0 onto the left, which is just positive 1. Then we draw our chart and write out the coefficients of our polynomial from largest to smallest degree. 1, negative 2, negative 29, and 30 in order to do synthetic division to figure out what factors with x minus 1. Next, we bring down the 1 and multiply by 1 to get 1. Negative 2 plus 1 is negative 1. Negative 1 times 1 is negative 1. Negative 29 plus negative 1 is negative 30. Negative 30 times 1 is negative 30. 30 plus negative 30 is 0, which is our remainder. Remember that when we get a 0 remainder from synthetic division, that means the value we evaluated is a 0, which we already knew from evaluating the function a moment ago. The polynomial can be factored by reading the coefficients, which will start with 1 degree lower than what we started with. We started with a polynomial of degree 3, so that means 1 degree lower is degree 2. So we have x squared minus x minus 30. This is all multiplied by our factor, which is x minus 1. From here, you can factor x squared minus x minus 30 into x minus 6 times x plus 5, as negative 6 and positive 5 multiply to negative 30 and add to negative 1, so that we have x minus 6 times x plus 5 times x minus 1. That means our three zeros are x equals 6, x equals negative 5, and x equals positive 1. Any of these three values plugged into our factored polynomial will result in a 0 for the function. This is the process you should follow to find all zeros if the polynomial has a degree of 3 or higher. If you have a degree of 2, you could just use the quadratic formula. You can sometimes factor by other methods, such as taking out a GCF or factoring by grouping, so always watch for that first. The hardest part is finding your first 0. Recall that I basically just told you that plugging in 1 would result in a 0, but in most circumstances, you will need to figure out the first 0 yourself. You can just guess values and plug them into your polynomial until you do find the first 0. Then you can do synthetic division to factor the polynomial. And it turns out we literally do need to do that. We have to guess and check to figure out what might be a 0 to get started. But something called the rational zeros theorem helps narrow down the numbers to check, so you aren't guessing anything and everything. The rational zeros theorem says that if p represents the factors of the constant in a polynomial, and q represents the factors of the coefficient on the leading term, the only possible rational zeros will come in the form p divided by q. This allows us to create a list of potential rational zeros for any polynomial to then plug in to see if they are true zeros. For example, take f of x is equal to 5x to the third power plus x squared minus 20x minus 4. P includes all factors of the constant of negative 4, and q includes all factors on the coefficient of the leading term, which is 5. The factors of negative 4 are plus or minus 1, plus or minus 2, and plus or minus 4. The factors of 5 are plus or minus 1 and plus or minus 5. P over q includes all possible ways the numbers in our p list can be divided by q. So we could have 1 divided by either 1 or 5, or the negatives, which would be plus or minus 1 over 1, or plus or minus 1 over 5. We could have 2 divided by 1 or 2 divided by 5, or the negatives, which would result in plus or minus 2 over 1 or plus or minus 2 over 5. We could also have 4 divided by 1 or 5, or the negatives, which would result in plus or minus 4 over 1 and plus or minus 4 over 5. This leaves us with 12 possible rational zeros. Cleaning this up a bit, 1 over 1, 2 over 1, and 4 over 1 can be simplified. Now note, if there are irrational zeros, such as square roots of things that aren't perfect squares, or perhaps imaginary zeros, those will not show up on your list. They will show up later when you start factoring. From here, you literally need to just guess and check. This is your list of possible zeros, so start plugging in values into the function until you find numbers that work. For example, the first number on my list is positive 1. I can go to my function and plug in positive 1 to see if I get a 0. f of positive 1 is equal to 5 plus 1 minus 20 minus 4, which simplifies to negative 18, so 1 is not a 0. You keep doing this, plugging in other numbers until you find one that's a 0. Now, if you have a graphing calculator like a TI-83 or TI-84, this is where your life gets slightly easier. There is an easy way to check numbers in bulk if you are allowed to use your calculator's table. On the TI-84, if you press y equals, go ahead and type in the function, 5x to the third plus x squared minus 20x minus 4. Next, press second and then window. Change independent to ask by hovering over it and pressing enter. You should only need to do this once. Now press second and then press graph. Now you can type in x values and the calculator will generate y values. So if I type in 1 and press enter, the calculator will evaluate the function at 1, which is negative 18, which we already got. So you can easily type in a lot of numbers from your list to see which ones are zeros. I usually start with the whole numbers, as they tend to be more likely to be zeros in most problems from textbooks. Let's try negative 1. Nope, not a 0. How about 2? Looks like 2 is a 0. That means, by the factor theorem, x minus 2 is a factor. To find out what it factors with, we do synthetic division. We have positive 2 on the side, as we always take what would be the 0 on the side in synthetic division. And then we have the coefficients, 5, 1, negative 20, and negative 4 from our polynomial. Bringing down the 5, we have 5 times 2, which is 10, 10 plus 1, which is 11, 11 times 2 is 22, negative 20 plus 22 is positive 2, 2 times 2 is 4, negative 4 plus 4 is 0, which is our remainder that we expected to get, since we already knew 2 was a factor. Our factored form can be read from the numbers at the bottom, starting with one lower power than what we started with. We have 5x squared plus 11x plus 2 times x minus 2. Now we can try to factor 5x squared plus 11x plus 2. We need two numbers that multiply to our a times c value of 10 and add to our b value of 11. 10 and 1 will do it. If we divide both by our leading coefficient of 5 and reduce, we have 2 over 1 and 1 over 5. Reading from bottom to top, we have x plus 2 and 5x plus 1, which are our two factors. Altogether, we have 0 is equal to x plus 2 times 5x plus 1 times x minus 2, if we set the function equal to 0 to find the zeros. We have x is equal to negative 2, x is equal to negative 1 over 5, and x is equal to positive 2 if we algebraically manipulate each factor to solve for x. If we look back at our list, we notice that all three of these values were on the list. If we were to get irrational or imaginary zeros, like I said before, they will not appear on the list. Let's try a few more examples. Say we have 2x to the fourth power minus x to the third power plus 4x squared minus 5x minus 30, and we want to find all zeros. Our factors of p, which is negative 30, are plus or minus 1 and plus or minus 30, plus or minus 2 and plus or minus 15, plus or minus 3 and plus or minus 10, plus or minus 5 and plus or minus 6, and the factors of 2 are plus or minus 1 and plus or minus 2. Our list of possible factors includes every value in our p list divided by every value in our q list. We have plus or minus 1 over plus or minus 1, which is plus or minus 1, 1 over 2, which results in plus or minus 1 over 2, 2 over 1 for plus or minus 2, 2 over 2 for plus or minus 1 again, 3 over 1 for plus or minus 3 3 over 2, plus or minus 5 over 2, plus or minus 6 over 2, which is just 3, plus or minus 10 over 2, which is 5, plus or minus 15 over 2, plus or minus 30, and plus or minus 30 over 2, which is 15. Now we notice we have some repeats on the list. We have 1 twice, 3 twice, 5 twice, and 15 twice, so we can cross the extras out. This is our list of possible zeros. Let's go to our TI-84 calculator to check some of the values. First, I go to y equals and type in the function of 2x to the 4th minus x to the 3rd plus 4x squared minus 5x minus 30. Next, press second and then the graph button, which brings us to the table. Let's try the numbers one at a time. And again, I usually start with the whole numbers. Let's try 1. Looks like that doesn't work. -1 doesn't seem to work either. How about 2? Yes, it looks like 2 is a 0. That means that x minus 2 is a factor, and we can use synthetic division to factor this polynomial. We have 2 out to the side, and the coefficients of 2, -1, 4, -5, and -30. Bringing down the 2, we have 2 times 2, which is 4. -1 plus 4 is 3. 3 times 2 is 6. 4 plus 6 is 10. 10 times 2 is 20. -5 plus 20 is 15. 15 times 2 is 30. -30 plus 30 is the remainder of 0, which we were expecting. We can factor as 2x to the 3rd plus 3x squared plus 10x plus 15 times x minus 2. Now there are two options at this point, depending on the problem. You can see if there is a way to factor what you have left to keep trying numbers from your list. In this case, it looks like we can factor the first part by grouping. We can pull an x squared out, which leaves us with 2x plus 3. And then we can pull out a 5, which leaves us with 2x plus 3. And we still have the x minus 2 factor. Altogether, we have x squared plus 5 times 2x plus 3 times x minus 2. We can set each part equal to 0 to find our zeros. The first part leaves us with x squared is equal to -5. Taking the square root, we have x is equal to plus or minus the square root of -5, which is the same thing as plus or minus I times the square root of 5, as the square root of -1 is the imaginary number I. For the second part, we can solve for x to get x is equal to -3 over 2. The last factor gives us a 0 of 2. Our four zeros are plus or minus I square root 5, -3 over 2, and positive 2. Note that we have 4 roots because we had a polynomial to the 4th power, which means we will have 4 roots. 2 of those roots are imaginary, meaning they are not real intersections with the x-axis, and the other 2 are real. Okay, let's try one final problem. We have f of x is equal to 5x to the 3rd power plus 8x squared minus 2x minus 3. Pause the video and see if you can find all possible rational zeros for this polynomial using the rational zeros theorem. Okay, hopefully you've given it a try. The factors of -3 are plus or minus 1 and plus or minus 3, and the factors of 5 are plus or minus 1 and plus or minus 5. That means the possible rational zeros are plus or minus 1, plus or minus 3, plus or minus 1 over 5, and plus or minus 3 over 5. Let's plug the function into our TI-84. We go to y equals, and then type 5x to the 3rd power plus 8x squared minus 2x minus 3. Now let's start typing in possible zeros. We have 1, -1, 3, -3. Doesn't look like any of the whole numbers worked, so let's try the fractions. We have 1 over 5, -1 over 5, 3 over 5, negative 3 over 5. Oh, looks like that one works, on our last chance too. That means the only rational zero is negative 3 over 5, or that x plus 3 over 5 is a factor. There is a nicer way to write the factor, as I'll show you in a second, but this is the form that we need for synthetic division. We write negative 3 over 5 to the side, and then write the coefficients of 5, 8, negative 2, and negative 3. We bring down the 5 and multiply by negative 3 over 5. 5 times negative 3 over 5 is negative 15 over 5, or just negative 3. 8 plus negative 3 is positive 5. 5 times negative 3 over 5 is negative 15 over 5 again, which is negative 3. Negative 2 plus negative 3 is negative 5. Negative 5 times negative 3 over 5 is positive 15 over 5, which is positive 3. Negative 3 plus positive 3 is 0. Our factor is 5x squared plus 5x minus 5. The other factor, coming from negative 3 over 5, can be found by setting x equal to negative 3 over 5 and then multiplying by 5. We have 5x is equal to negative 3. Adding 3 to both sides, we have 5x plus 3 is equal to 0, which is our other factor. Together, we have 5x squared plus 5x minus 5 times 5x plus 3. Now, we would ideally want to factor 5x squared plus 5x minus 5, which would require us to find two numbers that multiply to negative 25 and add to positive 5. But I can tell you right now, there are no such numbers. We will need to instead use the quadratic formula. We have negative b, which is negative 5, plus or minus the square root of b squared, which is 5 squared, minus 4 times a times c, which is 4 times 5 times negative 5, all divided by 2 times a, which is 2 times 5. Simplifying, we have negative 5 plus or minus the square root of 25 plus 100 all over 10. The square root of 25 plus 100 is the square root of 125. The square root of 125 is the square root of 25 times 5, which is 5 times the square root of 5, since 25 is a perfect square. Since negative 5 and 5 are both divisible by 10, we can reduce. We have negative 1 plus or minus the square root of 5 divided by 2. So the two zeros that come from the quadratic 5x squared plus 5x minus 5 are negative 1 plus the square root of 5 over 2 and negative 1 minus the square root of 5 over 2. Then, of course, we have the 0 from 5x plus 3, which is negative 3 over 5, which we found using the rational zeros theorem. Alright, my friends, that wraps up our video on using the rational zeros theorem to find all of the zeros of a polynomial.